Did put this record. Okay, I did put the kind of full explanation of this formula on my website with the question we did yesterday with it's a couple slides before with the 800-foot initial velocity and this bullets being shot straight up and straight down. But if you talk about that, if you look at that, hopefully you do because it's very useful, it's very informative. But we're doing another problem like that today. We did one yesterday where this term did not exist. Okay. In this PowerPoint, I stole this from a different textbook. This PowerPoint is using S of t instead of H of t, and you'll see that from time to time. H and S kind of flip back and forth. H obviously is a little bit more insightful because it means height. S maybe not so much insightful, but it means position. Okay. But for the most part, we can use H. So our general formula, H of t, is equal to negative 16 t squared plus an initial velocity t plus then an initial height. We call it H sub 0. They call it S sub 0. What we talked about in that video, if you watch that video from yesterday, I kind of explained where that negative 16 comes from. It's the gravitational acceleration, okay, or the acceleration due to gravity. And on Earth, it's different than what it is on the Moon and that kind of stuff, right? Okay. And even at different spots on Earth, it's different. Okay. The higher I am in the mountains, it's different. If I'm in a valley, it's a little bit different. Okay. But roughly negative 16 t squared is what we're getting there, and that's only the gravitational pull is 32 feet per second, so we take half of that, and we get 16. And there's a lot of calculus and Calc 3, Calc 4 stuff going on in there, and why that formula works. Okay. But this is initial velocity, so the problem will tell you that. Okay. This is initial height, and the problem they will tell you that. Okay. And we just plug things in, and we start doing our work. So here we go with an example. It says a ball is thrown directly upward from an initial height of 100 feet. Okay. So we're just throwing it straight up, and it should come straight down, right? All right. But if we measure that movement, the height of that ball against time, so the x-axis is time, the shape of that, those data points is going to be a parabola. Okay, so we got to first come up with our quadratic equation. So h of t is negative 16 t squared. Initial velocity, okay, 80 feet per second. And now it says we're going to do it from a height of 100 feet, right? So that means I'm standing maybe on a cliff or something like that, or top of a skyscraper or whatever, and I'm throwing this ball straight up, and I'm going to wait for it to come straight down to ground level. Does that make sense? Okay. And if you were to graph this, and we could do this on our TIA 384, maybe we will if we have time here at the end, but you see here that the initial time, when time is 0, okay, so we're only really worried about the first quadrant because time is positive, right? Okay. You see here that you're at a height of 100. You throw the ball up, all right, and that's going to come back down and touch the ground 100 feet below you. Okay, so that's the parabola that's going to be created against time. So we've got a couple questions here. It says give the function that describes this height in terms of t. So we've done that. Graph the function. So we graph it on our TIE 384. And then it says, the cursor in part B is at the point 4.8, 115.36. What does this mean? Okay, so they want to know what that point means. Okay, every point on that curve right now is a time, comma, h evaluated at that time. Okay, so usually like x and y values, right? Okay, but we like to use those terms instead because they're more informative. Obviously, t stands for time, right? Okay, and the h of t stands for the height at that time. Okay, so every ordered pair on that curve represents a time and then a height. Okay, so if this point right here is 4.8, okay, right here where that cursor is 4.8, comma 115.36, then what that means is at a time of 4.8 seconds, the ball is currently at a height of 115.36. Is that going to make sense? Okay. We're going to go through and we're going to find some other things about this curve that we're interested in. Okay. One of them is when does this curve reach its maximum height? Okay? When a curve reaches its maximum height is at the vertex. Okay? The vertex of any quadratic equation, okay, vertex is equal to the opposite of b over 2a, comma, h of opposite of b over 2a. Okay, so that's kind of the ordered pair that we're going to get.
Can I know what to choose?
Huh?
Can I know what
You can lay them right there. Thanks. So opposite of b over 2h, or 2a, comma, h, opposite of b over 2a. So what we're going to do is we're going to take this number, divided by, let's say, opposite of that number divided by 2 of those. Okay? See what that provides me, and that will be a time. So that will be the time in which we reach our maximum. We then plug that number back into the function, and that will tell me the height that the maximum is at. Does that make sense? Okay? So, plugging this in, finding the opposite of b over 2a, so it'll be what? Negative 80 over negative 32, right? Okay. Negative 80 over 32. And you're seeing there, they're doing the work on the smart board, but that gives you 2.5. Okay? We're now going to take that 2.5 and we're going to evaluate it inside our function. Okay? So if I evaluate that inside my function, where we've got negative 16, but now t is 2.5, so we have 2.5 squared. So plus 80 times 2.5 plus then the 100. We evaluate that, we get 200. Okay? So the vertex of this curve that looks something like that, okay? This highest point right now is at a time value of 2.5, and it's at a height right now of 200. Does that make sense to everyone? Okay. The next question they ask you is something to the effect of what interval is the ball, for what interval of time is the height of the ball greater than 160 feet? Okay. So greater than 160 feet, okay, first thing I want to find out is when is it equal to 160? Does that make sense? Okay. If I can find out where it's equal to 160, then I should be able to find out where it's above 160 and where it's below 160. So if I've got this information, and we know it reaches a height of 200, right? So we know then it has to hit 160 on the way there, correct? If they were to ask a question, and they did this in the one yesterday, if they were to ask a question like, when does it reach 300 feet? Does it reach 300 feet? No, if the maximum is 200, there's no way it's getting to 300, right? So it'd be no solution to that, and there's some algebra that would prove that to us eventually. Okay? So we're interested now, instead of this being h of t, we now have a specific value they want that to be. They want to be 160. Okay, so I'm going to subtract that 160 from both sides. Okay, so we get something like that, right? All right. Now a lot of these are kind of ugly in regards to factoring. So what we want to do is just go ahead and use quadratic formula. If we use a quadratic formula for that, we should be able to get the opposite of b plus or minus b squared. Okay, so b squared is going to be 6,400, right? 8 squared is 64, 10 squared is 100, so 6,400. Minus 4a is negative 16, c is negative 60, all over 2a, which would be negative 32. Okay? And that's what the time value that we'll get for when this thing hits 160. Okay? So, real quick, negative 80 plus square root 6,400 minus 4 times negative 16 times negative 60. Let's see. So that numerator gives me negative 29. But now when I divide by negative 32, I get a t-value of 0.918. Okay? Which tells me, and that kind of makes sense, if I'm at 100 feet and I throw this thing up with 80 feet per second velocity, then at 1 second it should be at 180 feet, right? So at a little less than 1 second, it's at 160 feet. Make sense? Okay. So that's one t-value. But now I've got to find out, so that was using the plus sign here. So now I've got to do the same thing with the minus. Okay, so we'll kind of cheat a little bit with our calculator, cut and paste, and that number. So that'll give a numerator of negative 130, and then we're going to divide by negative 32, and it gives me a t-value of 4.08. Okay? So going back to what this thing looks graphically, if we start here at 100, okay, we know at 2.5 seconds we're going to reach 200, right? Does that make sense, everybody? And now 160 would be about right there, correct? Everybody agree with that? And you see that if I put that line y equals 160 in, I intersect right there, and I intersect right there. Well, coming down, that point there, at y value of 160, is going to be a t-value of 0.918. Okay? That t-value there. Over here, okay, that t-value is the 4.08 that we come up with. Now they want the interval. They want the time interval. Okay? So how we write this? Okay? When it's 0.918 seconds, are we at 160? When it's exactly this time, are we at 160? Okay? Now, it says for what interval of time is the height of the ball greater than 160? So do I include this number? No. Okay? Because that's 160. Now I've done some rounding, but that's 160. Okay? Or provides a height of 160. We want a height that is greater than that. So we do not include 0.918. Okay? And for the same reason, we do not include 4.08. Okay? Because those are the times that give me exactly 160. But we want an answer that's greater than that. Does that make sense? Okay? If they said 160 or greater, then we put the brackets around the 0.918 and the 4.0. So that's the time in which our graph's above that. Does that make sense? All right, now they're going to ask, when does this thing hit the ground again? Okay? And we've already done something like this. I think those two questions are harder. Okay? Finding the vertex and finding when it's at 160. The next thing is they're going to say, when does this thing return to the ground? When they say return to the ground, they're implying what your y value should be. Okay, what y value should I have, or h of t value should I have when I hit the ground? 0. Okay, so they're saying instead of this being 160, it's now 0. Okay, and now we just do the quadratic formula again. Opposite of b plus or minus b squared minus 4 times a times c now at 100 all over negative 32. That'll be my time. Okay. Now, one of those time values that they give you back, I'm going to just, for the sake of time here, I'm going to go to the next slide and see if they actually do this. Okay. When we go through and do this, we should get 6.04 for one of these t values. And that makes sense, right? But look at my graph over there. Where does the other t value, where does this other side of our parabola, where does it cross the t-axis? What type of numbers are there? Negative. Okay? So you get a negative time, which mathematically is fine because the numbers in the equation doesn't really know that I'm dealing with time, right? It doesn't really know that, hey, he only wants the positive answers back. Okay? So you have to distinguish positive answers from negative answers when we're talking about time. Okay? So the only time this thing comes back to 0 is at that 6.04, which is one of those quantities when you evaluate them. Okay? The other one's going to be a negative something. Okay? And the other one is going to be, just kind of thinking about this. If this is that time is 6.04, and the vertex was at 2.5, okay? We should be able to do subtraction there. Find out what that difference is. 6.04 minus 2.5. It gives me 3.54. Does that make sense? So So the distance, what I just found, is that distance right there between the axis of symmetry for a parabola and one of the x-intercepts. And it's that distance that is green is 3.54. So can I take and subtract from this number 3.54 and find that other x-intercept over there? Okay. So when I take 2.5 minus 3.54, these two time values, without even evaluating this, I now know that these two time values were 6.04 and negative 1.04. That one we don't count because it's a negative time, right? Okay. That's kind of how we deal with those types of functions, those types of real-life situations with some algebra. And this is stuff that, you know, you might do this in physics when you guys shoot off your rockets. Okay? At some point you'll make rockets, and maybe, I don't know, maybe Mr. C used to make rockets with his class. I don't know if you guys do that lab still. But they would calculate this stuff, okay? You know, anybody that goes into the military and works with ballistics or anything understands this math, okay? And understands, I mean, we're just skimming the surface, but they do a whole lot more with this stuff. Because we would like to be able to shoot down a ballistic from North Korea at some point, right? Okay? So it'd be nice to make sure that those people that are doing this stuff understand this physics and understand this math to be able to do that. What I wanted to show you guys is how to use your calculator to do this. Okay? Because you're seeing here that that's a lot of what's going on in the PowerPoint. What I want you guys to do, get your calculators out, and you're just going to go to y equals. Throughout the year, you know, one of the goals that I have is for you to become a little bit more efficient with your calculator. Not necessarily let your calculator do the work for you, but to maybe enhance your work, to provide some insight to you that maybe you didn't have prior to using your calculator. So in y1, all I want you to do is type in negative 16. Now we don't have t's here, so we're going to use x, which is fine. Squared plus 80x plus then 100. Okay? Now if we graph this, and most of your graphs are going to be initially standard view, which they start you from like negative 10 to positive 10 on the y-axis and negative 10 to positive 10 on the x-axis. Okay? Obviously that doesn't get much of our picture in there, right? So we got to go mess with the window. Alright, so I need you guys to click on the window key. Okay? Now, we've already done some of the work here, and sometimes when you use your calculator, maybe you haven't already done all the preliminary handwork, like we've done on the whiteboard. So sometimes finding your window and finding a good window might be kind of trial and error, where you adjust the numbers, you go back to the graph, and you get the whole graph in, yes or no. If it's no, go back to the window, readjust, remanipulate the numbers, and then see. Does that kind of make sense? So it's back and forth sometimes. But we've already done a lot of this, so let's say the x minimum. I'm really not interested in anything to the left of the x-axis, or sorry, the y-axis, right? So let's just make our x minimum either 0, or maybe, I don't know, negative 1 or negative 2 or something like that. Our x maximum now, what was our vertex's height at? Or sorry, what was the vertex's, not the vertex, the x-intercept, what was its largest value? Say it again? Careful, I misspoke. What's these values? What's the largest x value that we had? It was this one, right? 6.04? Okay. So let's make our x maximum a little bit bigger than that. I'm just going to go to 8. Okay. X scale, all the scale means is this is how many kind of markings you're going to see on your axes. So you'll see 9 markings if we leave that at 1, right? I can change it to 2 and say it's going to put a mark every 2, and so forth. I think I can leave that at 1. Now my y minimum, okay? My y minimum I don't care about. It's not going to be negative. Alright, y values, I'm not interested in negative y values, right? But what we want to make sure is that when we go through our calculator, you see this stuff over here, these numbers? We don't want those numbers to show up on top of our x-axis, so we've got to push our x-axis up a little bit. So I'm just say my y minimum, I'm going to leave it at negative 10 and see if that works. Okay? But my y maximum, what was the maximum of the vertex? What was that height? 200. So I've got to change this to a pretty large number. I'm going to go to 220. Okay? But now my Y scale is 1. So what it's saying is that between negative 10 and 220, I need a mark for every integer between those. That's kind of unrealistic, isn't it? Okay. So let's say that we put, let's just go by 20s. Okay. And now we'll graph it. And that looks somewhat realistic, doesn't it? Okay. Now understand what this means because of the scales that we use. That's 0, that marking is 1, that marking is 2, that marking is 3, 4, 5, 6. Now on the y-axis, they're not going by 1s, right? We chose to go by 20, so 20, 40, 60, 80, 100, which is mimicking then that place that we stood on the y-axis and threw that ball, okay? The next thing we would want to do, if I want to see when this thing, I'll finish this video and do the calculator portion during third period today. About fell down. And put that on the website so you know how to use your calculator for the homework. Okay? Just finished